set up a little cron job. It will identify what day it is, so you know which class, and it will start, create a folder, start the recording accordingly, and do everything on its own.
Is it a fancy script?
It's not going to be very fancy, but after I have one whole semester taught through this interface, maybe next semester the same script will basically replay the appropriate clip from a previous semester, so I can just walk away. Or that thought had crossed my mind.
Then you can go home too. Log in.
Except the roll sheet will still be passed here. You guys can write some robot apps, to stay in the classroom and sign your name for you. All right. So let me check a few things. The recorder is recording, and I want to make sure it is recording from the right channel, because sometimes it does not. Okay, this is good. Everything checks out. All right, so we'll go back to Moodle first. And the first thing I will do is to give you a new homework assignment, even before we talk about the concepts that you will need to know for the new homework assignment. So that's a fairly typical format of my classes. I will tell you something about the homework assignment before we talk about the concepts. So this way, I think some people will pay more attention in the class, knowing that the material that follows will have something to do with the homework assignment. The name of this homework assignment is just called Mem1, okay, for Memory Access 1. So there will be Mem2 later on. Okay, Mem1 is really the first homework assignment that you have to do something. This is going to be a very general format, with questions and also assignments from this class. Download the file, upload it to the virtual machine using WinSCP. If you're in Linux, you can just use just SCP to transfer the file. You should upload it to the custom home directory, the one that you set up in the very first homework assignment. Then log in to the custom account with your name and run the following command with the home directory as the current folder, which is by default the case right after you log in. Then you have to run this command, assuming this file is already uploaded. Okay, this should uncompress the archive file and create a folder called mem1 with a single file mem1.s in it. Are we doing okay so far as the general procedure is concerned? Okay, you download the file from Moodle, you upload it back to your virtual machine, and then you go into the virtual machine and uncompress that file. It creates a folder. The folder has one single file, and that file is your homework assignment. The instruction to do this homework is actually inside the file itself. In other words, it is somewhat self-contained. I made it this way so that once you have that mem1.s file uploaded or uncompressed, you don't need online access anymore. Everything else you can do using the virtual machine with no access to the internet. If I keep the instruction here, that means when you're doing the homework assignment, you will still constantly need to have internet access. You can use a text editor to open and edit it, and there are two that are built into the virtual machine. There's VI and there's also Nano. I think you will find opening multiple PuTTY/SSH sessions to be useful, because you can open up one for the editor, open up one for the commands, and possibly open one up for man pages, just in case you need to find out how to use different commands. But be sure to save the source file before assembling, linking, and running, because otherwise the assembler will be using an old version of the text file, so the behavior of the program will not be consistent with what you actually write in the editor, because what you have in the editor is still in the buffer. It has not been written to the source file yet. When you're done, use this command in the mem1 folder to create the answer tarball. This is a little bit different from before. Okay, if you look through this command here, it is a little bit different. First of all, the extension of the file is tar.gz, which is the more appropriate name instead of tgz. This is different. Okay, -c space, this time it is a slash, not a tilde symbol anymore. And then in front of all the folders and also the names of the files that I want to include in the tar file, there's a tilde symbol at that point. This means that I'm going to record the full path from the root folder all the way down to the individual file. So this way I can more easily identify whose assignment I'm grading. Okay. It is okay to leave your executable and object files in the folder because my script will overwrite those files anyway. So it's okay, you don't have to clean up and remove all the files that you generate in the process. However, it is important to keep the names of everything. That includes labels in the source file, name of the source file, and so on and so forth, because my script will automatically look for those specific names. If my script cannot find those specific names, it will have to tell me, and I will have to grade your assignment manually. And there's one little bit about what happens when that is triggered. Once the answer tarball is created, download it to the host operating system and then upload it to Moodle. Grading for this homework assignment is for the most part all or none. Submissions that do not follow instructions will not get points even if the program works. Okay, so we are talking about simple instructions here. Follow the commands, do it this way, and so on and so forth. Okay, so it's not like, it's really, really hard. Has anyone taken cisp310, the Visual Basic Programming class? Would you say that there are more rules to that class than there are rules to this class? Sorry? Just a little bit? Okay. I remember when I stood in for Bob for cisp310, I had to spend 1 class and a half to explain all the rules that are applicable to all homework assignments, not just one, but all the homework assignments. And then I have to spend another day, another class on the rules for one single homework assignment that is specific to that assignment. Okay, are there any questions about this homework assignment? Let me open up this file, and I'm not going to do it the same way as what you will have to do. I will open it using, basically just an archive program or the archive program. And this part you don't have to copy, don't worry about it. If you want to open that file in Windows, you can use 7-zip to do it. 7-zip can open tar.gz files. And here we have this is inside the folder, and this is the source file that I was talking about. You have to change this program so that it will do whatever it's supposed to do. And let me change the font size a little bit so that we all see a little better. Okay, so I'll just read the instructions part. The objective is to replace the single question mark with a single direct operand. So this has to be very specific. It has to be the direct operand, so that the registered EAX will have a value of hexadecimal 54001245 at a breakpoint set to when a breakpoint is set to checkpoint 1. Checkpoint 1 is down here. This is just a label. So when I stop at this instruction here, I want EAX to have a very specific value. What you can do is only to specify a direct operand in place of the question mark here. You cannot do anything else. So the do nots, is a long list because basically you cannot do anything other than replacing the question mark with a direct operand. Are there any questions so far? Yep. Well, this is something that we will talk about today. So this is just a prompt, so that you guys will ask the question. So that's very good. Yep.
Is that the entirety of the assignment?
Yes. And you have 1 week, and you guys have 1 week to work on it. Yes. I think some of you, not the entire class, but some of you will feel that the pace of the class is going to pick up, and it will. Okay, this class does accelerate over time, which means the pace is going to increase by itself. Okay, so we are in topic 2 right now, and we're going to talk about addressing modes and memory allocation. And we'll spend some time to do this part too. This is a part that will take up a little bit of time. We'll only talk about the move instruction in this entire module. This entire module will basically go around or revolve around a single instruction. It is the move instruction. And no, I did not misspell move. It is actually MOV without the E. Okay, so that one extra keystroke E is going to cost enough time that the programmers decided, well, I think we'll abbreviate move to MOV instead of MOVE.
And jump. They just
Yeah.
got the unit.
Yep. In some other architectures, they go one step further, like MV for move and JP for jump. But in the Intel notation, they just drop one single letter for some reason. But then you have call just being call. Yeah, that's just very inconsistent. I do not know why. So in general, a move instruction looks like the following. Now, I'm not sure how many people are familiar with this type of syntax description. In this type of syntax description, if I use square brackets to surround something, it means it is just a placeholder. It is a token that will be expanded to something else. Okay? So when you see angular bracket SRC, that means that thing, the highlighted part here, has to be replaced by some actual source operand. Question?
No, I was going to say you said square bracket, not
But it is angular, yep. On the other hand, if I don't use the angular brackets, it is something that you have to type verbatim. In other words, the instruction has to start with MOV, so these three letters start the name of the instruction itself. When you see square brackets have their own use. When you see square brackets, everything inside the square bracket is optional, which means it does not have to be there. When you see the vertical bar, it means alternatives. So in this case, it means having a B, W, or L after MOV is optional. But you can only have one of the three if you choose to have a suffix to MOV. Is that okay? Okay, because this is a fairly standard way to describe syntax in programming. Yep.
So why do we need to put the BWL after MOV if it's
Well, that's part of the explanation later on. So the explanation of this syntax is described a little bit here, okay, which is just what I talked about. I did not read from my notes because that would be kind of boring. So that means we can have these four variants because we have move without anything in the optional part. You can have move B, move W, or move L because now those three other forms have the suffix. The two operands, one is called SRC for source and the other one is for destination. These two operands must be separated by a comma. So a comma has to be here between the two operands. An operand of an instruction is like arguments of a function. Okay, since all of you have taken cisp310 or a equivalent class, that means you should know what is an argument in the context of a function. What is the purpose of an operand or a parameter in the context of a function?
Pass it along.
So it can
Pass it along so it knows what to do with it.
So you can supply information, you can supply additional information to the subroutine so they can do its job. And it's the same thing here. In the case of a move instruction, you have to specify what am I moving from and where am I supposed to move it to. And therefore there are two operands. One is the source and one is the destination. The move mnemonic is a misnomer, okay, which means it is an inappropriate name. The name does not actually say what it is supposed to do. Because if you think about it, in the physical world, we can move. Okay, here's my dry marker pen. It was here, and now the dry marker pen is over here. Now that is an actual move because it's no longer here. Okay, but what about in memory location operations? If I go ahead.
I was just saying you're not actually moving the location of the bits.
Exactly. In other words, the source will not be empty, quote unquote empty, after the move operation. The original bit sequence will still be at the source. It's just that the destination will also have a copy of that. So that's why every time you see MOV as an instruction, in your mind you should think copy. Okay, that is really just copy. Okay, so moving on.
Is there a copy? Is the copy command just do something else, or is there actually no copy?
There's no copy command.
And that's just plain silly.
Yes.
Okay.
Good thing that my name is not on it. Yep.
It is kind of equivalent to passing by value.
We'll talk about the operands later because don't think in terms of C and C++ and Java. Okay, when you're talking about assembly language programming, we are talking about very low-level operations. So the concept of passing by reference, the concept of passing by value, the concept of even constants is actually fairly high level already. So in assembly language programming, we think in somewhat other terms. So we'll get to that part. We'll talk about the different types of operands, and in each type, like starting from here, I'll give you guys some examples. There are 3 types of operands. One is called immediate, one is called register, and one is called memory. Now, since I have this picture up already, it makes it kind of easy to talk about those 3 different types of operands. Okay. Now, this is the processor. Remember, this part is the processor. In order for the processor to know what to do, you need to have, guess what? An instruction. Okay? An instruction is basically just a binary bit pattern to be recognized by the processor, and then the processor, upon recognizing what the instruction is, will carry out the operation specified. The 3 different operands are fairly easy to understand once we have this picture. Let's talk about memory operand first. A memory operand simply means that the source or the destination of that operation lives here somewhere. Okay? The source or the destination is in memory. And that's why we have the name. It is called a memory operand. There are different types of memory operands too. There's direct, there's indirect, there's based and indexed, and there's base, scaled, and indexed. Okay, so there's a whole variety of memory operands, but they all have one thing in common. They specify a location in memory, and the content of that memory location is what you're processing, is what you're moving, what you're adding, and where you're storing the result. Okay? The second type is a register. A register operand is also easy to understand because we have this picture. Because a register operand just says, oh, I want to use this register here, or I want to use this register here. Okay? It specifies a particular register inside the processor. Immediate is a little bit kind of strange because it is neither a register or a memory operand. So where am I getting that information? How do I specify an immediate operand? Well, as it turns out, the immediate operand is a part of the instruction itself. Okay? In other words, in certain types of bit patterns as opcodes, you can actually specify and say, oh, I will reserve 32 bits inside the instruction binary bit pattern itself and say, this is the number that I want to use as the source of the move instruction. So are we doing okay so far with this picture? Okay, it is just kind of coincidental that I had this picture because I had to answer a question a little bit earlier, but it turned out to be a very good thing to have this picture because now I can indicate this is an immediate operand, this is a register operand, and this is a memory operand. Any questions about the 3 categories? Yep.
I know this is kind of wrong nomenclature, but should I be thinking that you can like a constant, or that it's something hard-coded in the software?
That's a matter of perspective. Because even though it is a part of the opcode itself, if you don't set up the processor to protect the opcode, you can actually override the opcode and hence change a part of the instruction, and therefore you change the immediate operand of the instruction also. Is it a good way to do things? No. But you can do it that way, and as a result, it is not exactly the same as a constant. Okay, so from our perspective as assembly language programmers, we should only remember that this bit pattern is a part of the instruction itself and not a register and not a memory. Okay? Yep.
In your instruction there, or in your picture, where is that location the instructions in? Is it some other kind of memory,
It depends on the instruction itself. Most of the time, the instruction would come in as a 64-bit chunk, and the immediate operand, I don't know for sure, but I would be guessing it is the least significant part of that.
But it's coming in from somewhere. It's not.
It is coming in from memory. All instructions have to come from memory. But when you execute the instruction, the immediate operand comes from the instruction itself. When you execute an instruction, a memory operand will still have to have a second access to memory in order to bring in a memory operand. So that's why memory operands are very expensive, because in addition to the memory access to bring in the instruction itself, you need a second access to memory to bring in the operand itself. Okay? No? Okay, go
So I was
ahead.
going to ask, like, what is an example of immediate, like, or immediate operand?
Well, that's something that we will talk about next. Okay, very good. Yep.
Actually, I have a related question. So in our last assignment, we put in our student ID, and then we checked the value to see if that was actually the value there. Would that be an example of an immediate operand?
Yes, that would be an example of an immediate operand. Okay. Yep. But from the look of the instruction, you cannot really easily tell, whether it is a memory operand or an immediate operand. When you talk about the syntax group, that will be clear. Okay. So are we doing okay so far with the three? Yep. Go ahead.
Oh, sorry, but just to make sure I'm getting it. So the instructions, with that, you could draw an arrow from the instructions to the register or the memory to show that they're calling those types of operands. Or never mind.
There will be, okay, when you specify a memory operand, a part of the instruction will specify the address inside memory. But it is only using that bit pattern as the address. So we'll actually go out to memory and go to that location and then bring back the content at that location. An immediate operand is used immediately, which means there's no dereference, there's no dereferencing, there's no access of memory whatsoever. Whatever this bit pattern is the value that you're processing. Good questions, very good questions. So are we doing okay so far with this? Okay. So we'll go ahead and talk about the first type, which is the immediate operand. An immediate operand, which is also called a constant operand in some contexts. But remember what I said, if you can change the instructions using a self-modifying program, then it is not really quite constant anymore. There are some architectures where the program space and the data space are entirely separated. Okay, so in those architectures, then instructions are definitely constants because you cannot change the instructions. It is not a part of the address space that the instruction actually can change. So is that okay with your question? Because in your case, when you asked that question, I kind of pointed out that in some programs, they use self-modifying code to change the instruction itself, but it is not possible in some architectures. Yep.
Yes, I have a question. What do you mean by a data space?
A data space?
Yes.
Okay, when you think about the execution, let's say, of a C program, okay? A C program has a very distinct separation of data from the code. Okay, program code like the assignment statements, your for loops, your conditional loops, the concept of a subroutine, returning and stuff like that. That's all code. That's all control flow stuff. But when you're talking about global variables, local variables, dynamically allocated memory and stuff like that, that's all data. Okay? So we have a very clear separation of code, which is telling the computer what to do, as opposed to the data space, which supplies the memory that is needed in order to store your variables, the objects, and stuff like that. Okay? In the Intel architecture, both code and data can coexist in the same space. So it is conceivable without the proper protection that you can write a program to overwrite instructions themselves. And sometimes people intentionally do that to make the program difficult to crack. Okay, Microsoft itself has written code like that so that the startup code of, I cannot remember which program, is difficult to crack because by the time you run the program continuously, it will be different from when the program was first loaded into memory. Okay, But in some other architectures, you cannot do that because code is in one space and then data is in another space. So in that case, it has some really nice advantages. Can anyone kind of guess what would be a nice advantage when your code, your instructions are coming from one space and your data is entirely separated into another space? Go ahead.
Tracing code.
Tracing code. Why would that give you an advantage?
So if it's like a bad code or whatever, you could debug it quicker, or
Not exactly.
You can open up two windows side by side, one that's exclusively data, one that's exclusively code, and follow instructions through the code window and see what's going on there while simultaneously watching or not the data window as needed.
Yeah, but even with a single space, you can still have two windows looking into different portions of that space. Yep.
you can read from both places at once.
Aha, that's it. Okay, because basically what happens is the processor now has two sides. One side to directly access the data space, and one side to directly access the code space. So that means when you read in the next instruction to execute, it does not interfere with writing something back into memory from the previous operation. Okay, so in terms of making the processor more efficient, it supports a better way to do pipelining. Okay, pipelining is a concept that I will not talk about in this class, but when you go take computer architecture at a 4-year university as an upper division class, then you will start to come into concepts or ideas like that, pipelining. Okay, when you have a data space separated from code space being separated from data space, pipelining becomes not only possible, it is also much more efficient that way. And that's why the the Atmel AVR architecture is a very fast architecture. As an 8-bit architecture, it is very fast. And also it's a very optimal architecture. It does not consume a lot of power for the processing power that it has. And part of that has to do with separating the code space from the data space. But that's kind of like a big digression. So now we have to kind of come back to what we were originally talking about. Okay, it is a bit pattern that is embedded into the instruction machine code. So when you look at the machine code itself, a portion of the bit pattern of the machine code is the immediate operand itself. As such, immediate operands do not use data memory at all. It does not use the stack. It's not a static allocation. It is just a part of the instruction. Furthermore, the value of an immediate operand cannot be changed in most situations, although it is very bad, as it is very poor practice to modify instructions in machine code when a program executes. Now, most of these newer architectures that we use these days, they have a particular bit to inhibit code execution in data space. Do you guys know about that? No? Yep, okay.
It's been around for a long time, and Intel finally just decided to re-implement it, call it something new, and people started using it.
Yep, but it is also, they reintroduced the concept because Microsoft could not stop Stack Overflow exploits and buffer overflow exploits. So one way to do it is in hardware, and basically you're saying you cannot execute code in data space. So that means you can overrun the stack all day long, you can overrun a buffer all day long, but since you cannot transfer control to those locations, then the exploits will not be effective anymore. Self-modifying programs exist for very specialized purposes, such as obfuscation. Okay, if you don't want some people to crack your program, then you can use self-modifying code, because in order to track the execution of a self-modifying program, someone will actually have to keep track of the entire state of the entire program all the time. They cannot just look at dump the memory content and try to understand the program that way. Immediate operands are only useful as a source operand because you cannot change it. So that's why they can only act as a source when you have the source and the destination. The access speed of immediate operand is super fast because it is a part of the instruction itself. It doesn't take any time to get to the value of an immediate operand. Okay, any questions about this slide? There's no example because I cannot give you an example using only an immediate operand. What will you do with just an immediate operand as an instruction?
Can you print it to screen?
No, printing to screen is a very long process in terms of assembly language programming. So it serves no purpose, and that's why there's no single example here to show you how to use an immediate operand itself. Now, the next thing is to introduce what is a register operand. A register operand is one that refers to the value of a register. We have 8 registers to play with in 386 enhanced mode. Most processors, such as the 386, has a small number of registers to store values to be accessed frequently in the near future. Okay? But it is not a cache. Okay? Remember, registers are not a part of the cache. They are completely different things. The reason why there are few registers are twofold. One, a modern processor uses general purpose registers, which means all registers can be used as the source or the destination. And that means there's one big switch has to be implemented in silicon gates in order to select any register to be input A and select any other register as input B. And that that's a lot of logic to switch the paths. And second, a register has to keep up with the speed of an ALU of a processor. And that's why you cannot have too many of the registers. In order for registers to keep up with this speed, they must be physically close to the ALU. However, so many registers can be placed close enough to the ALU that you can only have so many of those registers, and as a result, the number of registers is restricted. But we also talked about something else. We said, because the transistors are always getting smaller, we can now fit more registers than we could, let's say, 10 years ago. But we cannot change the number of registers, because if you change the number of registers, you will also have to change the format of the opcode. The binary code of each instruction will also have to be changed. Because in the past, let's say we only allocated 3 bits to specify a register as either a source or a destination. If you add to 16 registers, you will need 4 bits to select which register you want to use, which means the format of the instruction itself, the opcode, will also have to change. What happens when your opcode changes? What happens to backward compatibility in terms of software?
It goes away.
It goes away. Okay, and that's a big thing. Why do we know software backward compatibility is a big thing? Why do we know that? Why else are we still using the Intel x86 instruction set?
Because it works.
Because it's a good reason to turn a processor into a big heater.
Because
Yep.
it's very prolific?
No, not really. I mean, if you think about it, recompiling the kernel is easy. Recompiling, the GIMP, easy.
Because all the software out there is already using this, made for that.
Okay, let me give you one example. When the ARM32, the AVR architecture used to be an 8-bit architecture. Okay, so when they finally decided, okay, we like the instruction set, we like the way it works, but we want to make it a 32-bit architecture. So they came up with a brand new architecture based on the AVR, but the instructions are completely different. Okay, when they came up with that processor design, Atmel released the specification of the processor. Before they rolled out the first batch of actual chips, there was a port to Linux already. So people were able to run Linux inside a software emulator using the new architecture before the first chip was ever rolled out of the factory. So that really tells you, what happens with open source. Because if you have GCC already ported to a new architecture and you re-implement the kernel part, which has to be written in assembly, but a good percentage of Linux is written in C. So many of that can remain exactly the same. They are architecture independent. So they were able to roll out, a version of Linux for that new architecture before the processor was available for people to purchase. Okay, so let's get back to our point here. What about the Intel architecture? It's not because of Linux. It's because of what?
Because of Windows?
Because of Windows, exactly. Because of Microsoft and Windows, we have a big concern of backward compatibility. Okay, because you cannot just recompile a program. Why can't you just go ahead and recompile a program? I like GIMP so much, on the Intel architecture. I want GIMP with my, AVR 32-bit architecture. No problem. I download the tarball. Okay, I get all the tools that I need. I recompile GIMP, and now GIMP is on my new architecture. How come I cannot do that with Microsoft Word?
Because Microsoft is afraid that you're going to steal all their little secrets that don't work very well anyway and do something else with them. And then they won't be able to control how often your computer crashes.
Exactly, because it's not open source. The source code is not there for you to grab and recompile. Okay?
You got my point right there.
Oh, okay.
Microsoft doesn't use open source.
Exactly. So that really gives you an idea of the advantage of open source from the perspective of when you have a new hardware, a new architecture. Hey, you can have the software ready to roll before the hardware is even ready, and I think that is a really big strength of open source. The concept of open source. Now, but it seems like open source is a communist or socialist idea, which is completely counter capitalist, right? Okay, but if I were AVR, do you think I would support open source movement? Because I make the hardware, right? Do I care whether Microsoft wants to turn around and say, oh, let us also support your new architecture? No. If Linux supports it and I can sell the processor, I don't care. Right? In fact, I will hire a few, of my I will allocate a few of my engineers and say, why don't you guys help out the Linux community and write the back end, the Linux, the kernel drivers that actually require, a good understanding of the electronics or the physical properties of the processor, because the faster I make my new processor compatible with Linux, the faster people will start to use my processor. Is that making any sense? Yeah. And even though it seems like I'm losing money, contributing to an open source project, in the end, I sell more hardware. So there's no conflict whatsoever. Just ask IBM. Does anyone have the impression that IBM is communist or socialist? Communist. Yet they are the first. Of all the big companies, they are the first to use open source. They are the first to use Linux in a commercial setting. Well, not counting Red Hat, but Red Hat at the time was really tiny compared to IBM. Okay. So now that we know, why we are still using Intel x86 architecture, don't blame me for the rest of the class and ask me, why are we stuck with this archaic architecture? It's not my choosing. Okay, so are we doing okay so far with this? Why, even though physically we can have more registers, we cannot easily just change and say, oh, instead of 8 registers, now we have 16 or 32. So everybody is convinced that for some reason or another, we cannot just do that. Yep.
On the ARM architecture, are you still limited to 8 or whatever? You're not getting like 32 or 64?
They have a larger number of general purpose registers, but the number of registers is still set because of the instruction set. Because you still want somewhat of a code compatibility. But they don't have as much of a problem if they want to release a new architecture that is not binary code compatible with their old one. It's not a big deal. It's not a big concern, because most platforms supporting the ARM architecture are open source anyway. Like your cell phones, most of your cell phones use an ARM processor. Like with Android, what architecture supports the iPhone? Does anyone know?
Well, they make their own that's still technically ARM.
Okay, so it's an ARM core, but with other stuff on top of it.
I say that recently with iPhone 4, they made their own processor and branded it by them. I think it's still technically under the ARM category, but the ones they use like in the previous versions were older ARM processors.
Would it be opcode compatible? The new ones?
What's that?
Would it be opcode backward compatible?
Sure.
Okay. Okay, let's talk about memory operands. A memory operand is one that refers to the value. Okay, the key here is the value or the content of a memory location. Of the three types, memory operands are the slowest because you can see the distance between the processor and the memory. However, a memory operand can specify any one of the 2 to the power of 32 memory locations, and we are talking about a 32-bit mode of the processor. These days, with a 64-bit mode, then you have a whole lot more locations to address. Now, with the 64-bit mode of a 64-bit capable processor, you have potentially 2 to the power of 64 locations to access, each location being a byte. But tell me, how much RAM can you add to your motherboard?
4 DIMMs.
Not nearly 2 to the power of 64, right? 16 gig, 32 gig, okay? Most consumer type motherboards will support up to 16 to 32 gig. And even with a server setting, possibly they can support a terabyte, okay, of RAM, and that's about it. Okay, in other words, the software is now so far, the instruction set is quite a bit ahead of the actual physical capability of hardware at this point.
When that will we want it to be, so we can continue improving along that so it just can grow.
Yep. The 386 instruction set offers many different ways to compute the address of a memory location to access. Okay, so we will see this, today. We'll see at least a few of these, different modes. We will explore these later. A RISC architecture, on the other hand, will typically only support one way to access memory locations. It will be an indirect, type of access. We'll get to that part, when we, I'll tell you that when we get to that part. So we have just talked about the 3 main categories of operands, and now we can start to talk about how to allocate memory, and then we will also start with the addressing modes. Okay. Let's see, do we want to do this? Yeah, okay. A memory section is a contiguous area when a program is loaded as a process. When the program is executing, it is called a process. A memory section is basically, you have one section for code and one section for data. Okay, so for in this class, we can use a very simplistic view. We only have 2 sections, one section for code and one section for data. When you want to say, I want to put something into the data segment, you have to start with a dot data in your program, and then you can start to have some data definition. When you want to switch back to code, then you have to say dot text, and then you can put in some instructions. If you ever want to switch back and say, oh, I want to define some more locations, for my data, you can switch back to data again and define some more data locations or data definitions. In other words, these are basically just bookmarks. You have 2 sets of bookmarks. One set of bookmark for data and one set of bookmark for text, for the code. So when you switch, it remembers what was the last location that I used for data. Okay, when you switch to text, it remembers what was the last location for data. When you switch back to data, it remembers the last location for the code. So you can switch back and forth all day long, and it will still be able to keep track of the definitions. So even though in this case the 2 data portions are interleaved by a dot text portion in the source code, the assembler actually makes the 2 data portions contiguous in the data section. Okay, let me give you one example or one graphical illustration. Okay. So I'll start with a data definition here, and I'll just collectively call this chunk 1. I'll switch to text, and I have some instructions here. I'll call this chunk 2, and I'll switch back to data, and I'll call this chunk 3. Okay? So logically speaking, what the assembler would do is the assembler says, okay, I only understand there are 2 segments or 2 sections. One is the data section, and one is what we call the text section, which is actually referring to the code section. What it will do is it will say, I will put both data sections into here. In other words, chunk 1 and chunk 2 will both be here, and they will be continuous. They're right next to each other. The text portion, which is your code, will basically have chunk, oops, I messed up. This is chunk 2, this is actually chunk 3. Okay? So this means we can interleave, dot data and dot text all day long, but the program, the assembler, will still be able to piece everything back together in a contiguous way. Next slide. Okay. In terms of memory allocation, we have these constructs for memory allocation. A program can allocate memory from any section. In other words, you can define integers in either the data section or the code section. The difference is if you put it into the data section, it is somewhat like initialized variables, and you can change them as you run your program. If you put it into the .text section, they are still variables. They're still constants that you can access, but they're more like constants. In other words, you cannot change those because the code section is usually not writable. You can read from it, but you cannot write to it. We have the .int construct, and in this format here, we introduce something that is a little bit different from before. The curly braces here are only here for grouping purposes. In other words, when you see a pair of curly braces, they are only there to indicate a group of items. In this case, the group of items consists of a comma and a particular value. Now, since the value v is enclosed in the angle brackets, it means it has to be replaced by some actual value. This is just a placeholder for that. Now, what can I do with this entire block of code? Okay, remember, the curly brace does not tell you how you can use it. It simply defines a particular unit. The asterisk here is telling you can have any number of those. Okay, so that means in this case, .int has to be typed as .int. Okay, has a space here, at least one space. You can have as many spaces after that. Then a value has to be here. V1 has to be here. But after V1, it can be followed by any number of comma and then another value. Okay, so as long as you use comma as a separator, you can have a value, comma, a value, a comma, a value, a comma, a value, a comma, and a value. Is that okay? This is what this notation means. Yes. Yep.
So you're saying it has to have at least one value.
Yes.
But it can have multiple separated by comma.
Yes, it has to have at least one, but then after that you can have more. Optional. Yep.
And V1 is also value, not
So-
variable. V1 is also value.
V1 is also a value, yes. And in this case, all of these will be interpreted as 32-bit integers. Yep.
Those comma separated values, do they have to be spaced apart like the example?
No, the space is optional. This space here is optional. It's usually better to have a space, just so that it's easier to read. Okay. So in this case, each item or each value is encoded as a 32-bit number, which means if you specify a 0 here, it will be 0 represented in the 32-bit number. If you specify 1, it will be 1 specified as a 32-bit number. Okay? Because everything is going to be translated or encoded as 32-bit integers. The next one is called a dot word. Basically the same concept, except each value is now encoded as a 16-bit integer. If you put in a 0, it will be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 16 zeros. It will take up 2 bytes. The next one is dot byte. Well, I think you get the picture already. These will all be encoded into 8-bit integers. Now, if you try to specify a value that cannot be represented by 8-bit, it will just truncate it. It will only use the least significant 8 bits, and the most significant part will be just tossed away. Yep. Can you speak up a little bit?
I said, what do you mean if you can't show it in the 8-bit? Like if you put in a number, like a 2-digit number, and you can't show it 8 times, you'll cut it off a thing or something? What do you mean by that?
Any value can be represented in any base. So you specify a value, and it will use 8-bit to represent the value that you type in. Okay? And you can use base 2, you can use base 8, you can use base 10, and you can also use base 16 to express what value you want to be encoded as 16-bit, 32-bit, or 8-bit quantities. Okay. The next one is .ascii. .ascii will allocate and initialize memory locations for what we call a string in your C class, represented in ASCII, 1 byte per character. In other words, it is not Unicode, it is just plain old 8-bit ASCII code. A string is quoted by the single quote symbol.
Did you skip .fill?
What? Oh, .fill? Yes, I did. Sorry. I kind of warped ahead of myself. Okay, .fill is a little bit flexible. It let you specify a particular pattern. So if you look at this syntax here, it looks kind of confusing. .fill, .fill has to be typed verbatim, has to be just like that. The first thing you specify is a count, how many of something, okay? And you can specify just this much, .fill with a count. What that will do is it will have defaults for the rest. But let's first take a look at the full format, and then we'll talk about the default in case you do not specify the rest of it. The size here refers to the number of bytes per item. In other words, if you specify 1, then everything will take up 1 byte. If you specify 2, then everything will take up 2 bytes. If you specify 4, everything will take up 4 bytes. The value is, I missed a close angle bracket here. So there should be a close angle bracket at the end. The value is basically just, how do you want to populate this chunk of memory? Okay, let me just spell this out. How many of this type of bit pattern using what number of bytes should I put into memory? That's basically what it's saying. Is that okay? Now, but what if I just specify the first 2? What if I don't specify value? Value by default is 0. What if I only specify this part here? What if I don't specify the size? Then by default size is 1. In other words, if I say .fill 200, it will allocate exactly 200 bytes and have those 200 bytes initialized to 0. Is that okay? If I specify .fill 200, 2, it will actually end up allocating 400 bytes, but the 400 bytes will be will also be initialized zeros. You don't have to be too concerned about .fill at this time because we don't have .fill in the homework assignment. Yep.
What is the size of value?
What is the size of value?
Yes,
You
how
mean
many
here?
bits wide is it?
It can be any width, because it will just be truncated according to the size.
So if you use like an 8-bit size and a 7-bit value,
It will just have a 0 to fill in the most significant bit.
okay.
Yep. Yep.
Does memcopy call fill?
Sorry?
Does memcopy call fill?
No.
You use memcopy?
No. It's a concept related to memcopy because memcopy also allows you to specify, similar parameters. But this actually has more to do with pre-initialized static memory. You're just specifying a pattern of memory locations to be initialized. Okay, and then we have ASCII. ASCII is just allocating byte for byte by byte, but you can specify the ASCII code instead, because otherwise it will take a long time to spell out a sentence if you have to use the dot byte and then you have to specify character by character by character. This is just a shorthand to allow you to enter like a sentence pretty quickly. And then the last one is .asciis. Okay, the last one is different. I'm missing a dot at the beginning. There should be a dot before the ASCIZ. I'm looking at the watch because if I have enough time, I will go in and actually go ahead and change my note and fix all these things. But since I may not have enough time, I'll just kind of have to remember to go back and change it later. Now this one is similar to ASCII, except the entire string will also have a null terminator at the end. Okay? In other words, if I say .asciz, double quote, or quote TAK, and double quote, it would actually allocate 4 bytes. First byte will be the ASCII code of T, second byte will be the ASCII code of A, ASCII code of K, and then a 0 as a null terminator. And now we have labels. One of the convenient features of using an assembly language is we can use labels. A label can be defined just like this. A label name, and then followed by the equal symbol, and then followed by a value. A label can be anything. So don't look at label as macros. Don't look at labels as labels in C. Don't look at labels as any concept that you already know in C and C++ programming. All a symbol is it is 1, a symbolic name, and 2, it has to be resolved at some point to a numeric value, a bit pattern of some kind. And that's all there is to it in symbols in assembly language symbols in assembly language programming. So I can give you one really simple case. 3, THREE equals 3. So that means every time the assembler sees 3 THREE as a symbol, it will basically say, oh, okay, you mean the number, the numerical value 3. Okay? You can also define some stuff like this. You can say 6 equals to THREE plus THREE, because once you have this definition here, then the assembler will say, oh, whenever I see THREE, I will equate that to the numerical value 3, and do the same thing here. Then this becomes 3 plus 3, and it will come up with a numerical value of 6. So now we are actually equating the symbolic name SIX to the actual value of 6, the value 6. Okay, are there any questions about defining symbols? Okay. Now we have also a concept called the current location. This is not something that you really have to know, but it is a very handy thing to use sometimes. As you define data entries, the current location will change. Okay, let me just give you one quick example here. Or maybe I should use the text editor so I can, 1, do it quicker, and 2, capture it. Capture that so we can save it. Okay. Okay, so I'll use the pound symbol to represent, comment. Okay, at the beginning, all counters start with 0. So the dot data has its own counter, which starts at 0, and dot text has its own counter starting at 0. You type your dot data, switch to data section, and start with 0 at this point. Okay, and then you can say dot int, and we'll say dot int 23. Okay, so this uses up 4 bytes. So at this point, from the perspective of the assembler, at this point, exactly where the comment is, where is the location counter? The location counter has a value of 4, because I just used up 4 bytes for the dot int construct. Is that okay? In other words, the location counter is an internal variable that you really don't have any, well, you do have some control over, but for the most part, it is hidden from you. You don't really access it directly. Okay? So just to continue with this example here, if I say dot word 1, 2, 3, just like that, that will use up 6 bytes. Because one dot word will take up 2 bytes, and now I have 3 of those things, it would use up 6 bytes. So that means at this point, the location counter has a value of what? 10, exactly. Now switching to dot text and do something over here, okay, and then switching back to dot data does not change it, okay? Because when you switch back to dot data, it will switch back to its own location counter. So I can say at this point, the location counter of dot data is still 10, even though I might have defined something in the code section, but since each section has its own location counter, I can switch all day long and it won't change the location counter of the other section. Are we doing okay so far with this concept? Yep. yes, you can use the dot notation. Okay, so I'm switching back to the note here. So the current location counter is represented by a single period, a dot. Okay, so that means if I want to, okay, if I want to use a label to remember the location of the following allocation, I can do this. Okay, so basically I can say I define the label first. Okay, I can define the label as tag Aoyang, and I can say tag Aoyang using the equal symbol and then use the dot. In other words, I am telling the assembler and say I want to define a symbolic name called TAKAUYEUNG, and I want that to be the numerical value that equals to the current location counter of the data section. As a result, I just define the label, but this location is not the location of the previous definition. This location has not been allocated yet at this point. This is the next available location. Is that making any sense? Okay, let's do some counting here. We already know that the location counter of dot data is 10, right? And we also know that we have just allocated 10 bytes in the dot data section, right? So how do you count those bytes? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So location 10 has not been allocated yet because we count from 0. Okay, so remember that. So now if I go here and say dot ASCII and say my name, okay, this will use up, okay, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This will use up 11 bytes. So the location counter is now at 21. But the label tag Aoyang is going to be at what? It's at 10. 10. Because the current location is 10 when I run into this definition. Is that okay so far? Kind of? No? Okay, go ahead.
Put the ASCII constant Aoyang above where you define the dot right there?
Then I would be, okay, if I put this ASCII line ahead of the symbol definition line, then the label will be defining the location right after the last byte here. In other words, the byte that is right next to the ASCII code of lowercase g will be the label definition.
So that would be 21.
That will be 21, yes. Okay. Are there any questions at this point? Is this still okay? Yep.
So does dot point to T? Is that what it points to? Or I mean, does tag A9 point to the first letter T of your name? Is that what it is?
Yes. It's kind of like a tricky way to say it, because I don't want to use the word point to. Tag Aoyang as a label is a number. That number turns out to be the memory location of the uppercase T of this dot ASCII definition. Okay? It doesn't know the length. It only knows that it is the same as this location. Okay. So switching back to the notes here. In other words, I can do something like this, which is very close to what I'm doing in the example. But doing this is very cumbersome. Okay, every time you want to define a label to be the current location of a section, it is kind of cumbersome to have to say equals dot equals dot equals dot. So an alternative to do that is simply to use a colon to represent exactly the same thing. So when you look at these two lines and then you look at this line here, they mean exactly the same thing. It's a shorthand. This is a shorthand of the other form. Are we doing okay with this one? So we are slowly getting into the material that you need to do your homework assignment. Okay, so this stuff here is already starting to get into it. So we have just covered all of this stuff here. And now we can start to talk about the immediate operand, the register operand, and also the direct addressing mode operand. The first one is the immediate operand. It is, what we just have discussed earlier. And the syntax of doing that is you have to start with a $sign. When the assembler sees a $sign, the assembler will say, okay, whatever expression or whatever the value of the expression is following the $sign will be the bit pattern that it will put into the instruction as the immediate operand. Is that okay? No? Okay, remember what an immediate operand is? It is a part of the instruction itself. It's a bit pattern inside the instruction itself. So what this is the assembler, from the assembler's perspective, it is triggered by seeing a $sign in front of an expression. In this case, I have a very simple expression. The expression is simply 0. So that means a part of the instruction will have the bit pattern for 0. Now, I know we haven't talked about the push instruction, but for this example, I'm just illustrating how do you specify an immediate operand. You start with a $symbol. Yep.
Does that mean if you're doing immediate, that the 0 would never be replaced by a label? Because then that would have to access memory?
This has nothing to do with accessing memory because it's an immediate operand. It is a part of the instruction itself. Let me move on to the next one. I think it will be helpful to see how it can be combined with a register operand. Yep, go ahead.
Sorry, so do you have to tell the assembler what sort of operand you're giving it?
No, this is already enough clue to the assembler. So if you start with a $sign, it is an immediate operand. The assembler understands that. The next one is a register operand. So the register output, for this purpose, the registers, there are a whole bunch of registers, and I may not have enough time to go over, to get to the direct operand. Let me see if I can I cannot skip. Okay, this is how it looks like. I've never really drawn a picture inside, my note here. The text describes the same thing. It is just easy to see a picture. Okay, we start with AL as a register. AL as a register is 8-bit wide. Okay, in other words, there is such a register in a program called AL. It is an 8-bit register. There's another register called AH, which is also 8-bit long. Okay, is that okay? So now we have two registers. One is called AL, one is called AH. They are different registers. Each one is 8-bit wide. Sometimes you don't want to refer to an 8-bit register and then another 8-bit register. Sometimes you want to see the whole thing as a 16-bit register, right? So if you want to see this whole thing as a 16-bit register, you call this AX. In other words, when you refer to AX, it is actually using AL as the least significant 8-bit, and it's using AH as the most significant 8-bit of the 16-bit quantity. Are we doing okay so far with this? Yes? Okay. Now, if you extend it out and add 16 more bits to it, and you say, I want to refer to this entire 32-bit register as one single thing, then it becomes EAX, which is a 32-bit register.
Is there a name for the 16-bit part?
No, this part has no name, and therefore there's no way to access it individually. That's a very good question. Okay, are we doing okay so far? We have AL. Yep, go ahead.
I was just going to ask, so you can refer to the first 16 bits as either 2 8-bits or as one whole 16, or then you can extend to a 32, but you can't have two 16s.
That is correct. You can have the least significant 16-bit and call that AX, but you have no access to just the most significant 16-bit of the 32-bit register. Yep.
Are these actual register names, or did you just pull kind of out of a hat? I mean,
They are actual register names. Okay? And there's A, there's B, there's C, and there's D. Okay? So you can see you have BL, BH, BX, EBX. You have CL, CH, CX, ECX, and then you have DL, DH, DX, and EDX. Okay, they basically can be partitioned exactly the same way.
So we have 4 sets of basically that setup right there.
Sorry?
We have 4 of those setups right there.
Correct. Yeah, you have 4 32-bit registers. Each one can be broken up like this way. And then you have 4 additional registers. One is called ESP for stack pointer. One is called EBP for base pointer. One is called EIP for the instruction pointer. And there's one more, which is the status register. I think it's just E flags. These 2 we cannot access directly, so we won't deal with these 2 directly. In this class, we'll only get to ESP and EBP. There's also ESI and EDI, but we don't use those either in this class. So we'll just use EAX all the way to EDX, and then these 2 are special. So don't touch ESP and EBP until we get to that particular section of the class.
How big is ESP and EBP 60 bits?
They are all 32-bit. All registers that start with an E name, E letter, are 32-bit registers. Okay. Yep.
What is a 64-bit register?
I do not know.
Starts with that.
If you run the assembler on a 64-bit architecture, and then you say IR info registers, it will show you the names of the 64-bit registers. I cannot remember offhand. Okay. Now, when you want to specify a register in an instruction, you always have to precede the register name with a % symbol. Okay? The % symbol as a prefix tells the assembler whatever follows is the name of a register. And you have to follow those rules exactly, because if you don't have a % symbol here, then it means something else. Okay? So now we have 2 prefixes so far. We have the dollar prefix, meaning immediate, and then we have the % prefix, which means the following is a register. Okay? So I'll just go ahead and move on to the next one, just so that we have covered all the topics. Not quite enough for you for some of you, you can do the homework assignment already, but some of you may want to kind of do some studying, do some reading, and then you can play with the program. I mean, nothing bad really can happen, but you can just play with the program. Okay, now we have direct addressing mode, which is the last piece that you need for the homework assignment. A direct addressing mode means, in this case, this is our direct operand. The first 0 is not. How do I know the first 0 is not a direct operand? Because of the $sign. So with the $sign, what type of operand is it? Immediate. Is an immediate. Very good. The second one without the $sign is a memory operand. What it means is I want to specify location 0 in memory. Okay. Now this is really kind of strange, because what this instruction will do is a move instruction. Now, the move instruction without an L or a B or a W to specify how much stuff you want to move, by default, it is 32-bit. Okay? So by default, the default width is 32-bit or 4 bytes. In other words, this is saying I want to move 4 bytes. From where to where? The first operand is our source. In this case, the source is an immediate operand, which means I want to move the bit pattern 32 zeros as a bit pattern to a destination. The destination is 0, which means location 0 in memory. When you execute this instruction, it will attempt to zero out the content of the first 4 byte in your memory space. Is that okay? Now, I said and emphasized attempt, because location 0 is protected. You are not supposed to change that location. Now, since Linux is running in a protected mode, that means the operating system will say, oh, Mr. Application Program, you can only access this memory here. if you try to access memory beyond what you're allowed to, it will give you a little slap on the hand. And how do we call the little slap on the hand in Windows?
Blue screen of death.
No, not quite the blue screen of death, but there's another name for that. A segmentation fault. That's the Unix name. What is the Windows name for that?
Crash. Fatal exception.
I cannot remember. General protection fault. That's it. Okay. So for 20 points, for 20 points you get this answer. But you're reading ahead of me. That's good. So GPF, or general protection fault, is the name of that. When you try to access something that you're not supposed to, in Windows it will be reported as a general protection fault. In Linux or Unix land, it is usually called a segmentation fault, which is also abbreviated as seg fault. Okay? A seg fault usually means that a process attempts to access memory location that it has no permission to access. Okay? And we have one. I know we're running out of time here, but this is really quite useful. In general, we don't need to use a numerical constant for direct operands, so what we usually do is we use a label. In other words, here we have a program, .data label1 : .int 0x5 is going to do several things. One, we switch to the data section. Everything in the data section can be initialized to begin with, but you can also change it later on if you want to. Okay? In other words, these correspond to quote-unquote global variables when you look at it from a C method, from a C perspective. So .data switches to the data section, which means I'm going to define some entries in a section of memory that is intended to store variables. I start with label1 : which means I'm defining a label called label1 as the very first location in the data section. On top of that, after I define label1 to be the first location, then I say, oh, I want to use the first location and the next 3 bytes to be initialized to the binary representation, the 32-bit binary representation of 5. So that's going to be a whole bunch of zeros, and the last bits will be 101 because it's 5. Are we doing okay so far with this? Then we switch back to the text section to specify code. Anything that you can execute, you should put it into .text, even though you don't have to. So somewhere along this line, we encounter this instruction here: move MOV without the L, which means the L is implied. If you don't specify B, W, or L, the L is implied. So this is a 32-bit move instruction. The first operand, which is the source operand, is 23 in decimal, which specifies 23 as a 32-bit quantity or bit pattern. We'll move that, which means we're copying that to the memory operand label1. Now, from the assembler's perspective, label1 here will be replaced by the actual value of the location of this int 5 here. Okay? So what this instruction will do when you execute it is this bit pattern here will be interpreted as the address of where I am supposed to store 23. Are we doing okay so far with this? Kind of?
So is it essentially saying label 1 equals 23?
Yes, vaguely. Okay, yeah, vaguely, because we don't really have types in assembly language programming. Okay, so all it is doing is to store 23 to the location indicated by this expression. This expression turns out to be the location of the .int5. So it is going to overwrite the 32-bit that used to represent 5, and now after this instruction, it will be representing 23. Yep.
What do we have in front of 5, 0 and x? What does it mean?
0x is the prefix of hexadecimal.
Oh,
Now, in this case, obviously, it does not matter because 5 is 5. Yep.
So now 23, if it's overwriting basically what label was, its new position would be a .data at position 0 to 3, right?
Well, the 0 is somewhat misleading because even though from the assembler's perspective, it is location 0, by the time your program is linked and by the time your program is loaded into memory space to really execute, it won't be location 0 anymore.
Okay.
but the loader, along with the linker and everything else, will automatically fix up the location so that from your perspective, you don't have to worry about a single thing, because as a symbolic name, the tool chain will make sure that this label 1 will always refer to the memory allocated because of the .int. Okay. Even though the actual location when you run the program is not going to be 0. Now, if you guys don't mind, I will spend the next 2 minutes to actually go through a sample program like this, so that you can see, what it, is going to do. Yep.
So the label won't remember like what type it is.
There's no type. There's no such thing as a type. Okay.
And also, for example, if you are just like doing label 1 colon like word.
It is not a type. Okay, when we specify .int, it is not the same thing as int5 in C. Even though you might think that, oh, that means int5. This means int label 1 equals 5 in C. No, it does not. Okay, label 1 has no type. The bit pattern, a whole bunch of zeros and then 1 0 at the end, has no type. Okay, the memory operand here, label 1, has no type. There's no type wherever whatsoever when you write a program in assembly. Yep.
So, loosely speaking, could you say that would be equivalent to a void pointer then?
Not quite a void pointer either. It is just a pointer of no type that you can use for anything. You can look at it as a void pointer, but at the same time, you do not need typecasting to try to look at it as something. Okay. Okay, so what I'll do is I'm going to spend the next few minutes to just go ahead and illustrate this little example. So I'm going to write a program to quickly illustrate this one. I will change to today's folder, so in case I remember to upload, everything will be in this folder here. Let's see. I'll just call this test.s. Okay, so I have .data here. And I'll just kind of follow the program that I have earlier. Label 1 colon .int 0x5. Switch back to the text section here. Now this part here, don't worry about it. It's just stuff that I have to do to get the program to work. And I will have a no op. And then I have a move L $23 to label 1. And that's the end of the program. Okay, the rest of the program is just boilerplate. The no op here, the NOP, is really just a filler because I cannot put a breakpoint on the very first instruction to stop the program from executing. So that's why I need one instruction that does not have any meaning so that I can actually stop at the instruction that I want to track. Okay, so that's my program. And the first thing is to assemble it. And then we link it. And then we can use GDB to debug the program. Now, before we debug the program, let's take a look at what is actually in test.o and test as an executable, because they will tell us about the label definition too. Okay, now let's see. It's going to be object dump, if I remember correctly, and it has a whole lot of flags. I want to do a -d disassemble and test.o. Does it say anything about the location? Nope. Okay. I want to see whether I can -t. There we go. Does it define the locations? Yep. Label 1. Okay. This is the definition according to the assembler. Label 1 is defined to be a label in the .data section, and its value is all zeros. Okay? We can do the same thing to the executable, and inside the executable you can see that it is exactly the same thing. Label 1 has a value of 0. Now, when we use the debugger to run the program, it is not going to be the same thing. Because when you run the debugger, you can also check what is label 1. But when you check label 1, you have to say print and ampersand label 1. And you can see that label 1 is actually not 0 anymore. That's because when you run a program, the loader, which is a part of the Linux operating system, will have to find a place to fit your program. And that place to fit your program is not going to be location 0. But the loader will not only just decide where to put your data section, it will also go back and change your executable and to make sure all references to label 1 will also be pointing to exactly the right location. So you don't have to worry about a single thing because everything is automatically adjusted for you. Okay. So when we run this program, the first thing you can do is to examine the location of label 1 and see what it is defined at this point. Now you can use several commands in the assembler that can be useful. One is the X command for examine. If you need any help, you can always say help X, and it'll give you a very terse but complete explanation of the command. So we can say X/, in this case we want to use a W to specify 32-bit. In hexadecimal is X, and then we supply the actual label, and it tells me it is 5. That's good, right? I can use L to list the program. I put a breakpoint on line 7, which means the program will stop before line 7 executes. I run the program, and it stops at exactly the right place. I can now take a look at label 1 again, or the location label 1, and make sure I still have 5. It is still 5. Are we doing okay so far? I single step, US to single step, which means I only want to execute one instruction and then I stop again. Okay, so that one instruction of line 7 has now executed. It is time to look at the location of label 1 again, and it is now 17. That's wrong. 17 is not 23. Yes, it is.
It's an 8-bit, right?
It is hexadecimal. Okay? Because in hexadecimal, this 1 means 16. 16 plus 7 is, in fact, 23. So we got everything back. So this is a very simple program to illustrate that particular aspect of what is an immediate operand and what is a memory operand. Okay? Do we have any questions at this point?
You still recording?
Yep, it's still recording. Yep.
So the label is a memory operand in that example? Label one?
Correct. Okay, let me just go back to the program itself. When you refer to, you're referring to this part here.
Right.
When you don't see a %, it is not a register. When you don't see a dollar symbol, it is not immediate. The only choice left is it is a memory operand.
And that's also what you're calling direct accuracy.
This is a direct operand, and what it means is this can be label 1, which is a very simple expression. It can also be label 1 plus 2 times K2 times the whole thing times K3, and then you divide the whole thing by K4 and so on and so forth. It can be a huge long expression, but nonetheless, the value of that entire expression will be treated as a memory location. Okay, so remember that. It doesn't have to be label 1. It can be label 1 plus whatever. It can be label 1 minus whatever. It can be label 1 divided by something. It can be any expression. The point is the value of the entire expression. It can be simple, can be complicated, but the value of the entire expression is treated as a memory location.
So they're the same. If you call something a direct operand and a memory operand, they're the same thing.
A direct operand is a kind of memory operand. At this point, it is the only one that we have talked about, but then in the next class, we'll talk about the other gazillion types of memory operands. Yep.
Okay, right now label 1 is at location 5, and then we add 23 bits to it, so it's going to be 28.
We're not adding anything. We're copying. Okay, this is a copy instruction. So we are copying the bit pattern for 23 to overwrite the locations specified by label 1. Okay. Yep.
Will the code be like override, like on the allocated memory? For example, if on the variable on the top it is label like label 1 dot like word, and down here you're just
okay, that's a very good question. The question is, what if I change this to .word? That's a very good question. If I change it to dot word, that means only 16 bits or 2 bytes are allocated. And yet I'm going to overwrite 32 bits or 4 bytes. So that means I have 2 bytes that are not accounted for that I will go ahead and overwrite anyway. So I can tell you right away the program will not crash, because when you allocate memory, it can only allocate in certain increments, and 4 is not the minimum unit. I think the minimum unit is like 16 or something like that. So the program is not going to crash because it will still allocate enough memory and say that your program can modify that chunk of memory. It's just not a very good practice to do it. And guess what? If you change a program like this, it will still assemble. You try to do something like this in C or in a reasonable environment, it will come back and warn you and say, oh, but you just allocated 16 bits. You cannot overwrite a 16-bit location with 32 bits. In the assembler, it does not care, because guess what? When you specify move L $23 to label 1 is only specifying the very first instruction. It does not understand that it does not have enough width to store the 32-bit source. Okay? Any questions? I think we should change this class format, so that if necessary, I can turn the lab portion into lecture too, so we can have a 3-hour lecture, whenever we need to.
No offense.
Hey, it's all going to be recorded anyway.
So those last couple of lines were just moving 1 and 0 to registers?
I'm sorry, say that again?
I was just saying the last couple of lines were just moving 1 and 0 to registers?
Yeah, this is just the normal exit instruction set, which is basically, it's telling the operating system, I'm ready to go. That's what the last 3 instructions are saying. It's exit 1. It's exit 0 in the context of a C program. Okay, so let me stop the recording first, because I think we can probably stop at this point. Uh-oh. Am I actually recording?